Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Hi class, welcome back to SIC 1004/SES1230. We are going to pick up where we last stopped our lecture, and we're going to continue with our discussion on thermodynamics. Now, before that, I would like to remind you to scan your attendance, which is actually up in Spectrum, and make sure that when you actually write your matrix number, make sure that you also include the slash number. If you don't include the slash number, it's not going to record your attendance. So there were a few cases, there were many of you actually who didn't actually put the slash number, and so that is problematic. So make sure that you do that. So it's very straightforward. Just record your attendance according to the list of names that I actually post in WhatsApp. So use that matrix number with the slash number, okay? And I hope that is clear. And make sure that you do that after you have gone through the slides, gone through this video, and then you record your attendance, and it has to be recorded today, okay? Otherwise the date stated when you actually record attendance will be on the day of when you actually record. So make sure that it's today, so that in accordance to today's class. So the other thing that you also need to do is to complete the entrance survey. So this entrance survey is actually it's a questionnaire to ask how much you actually know about this particular subject, or for any other classes for that particular subject, and at the beginning of the session. So towards the end of the 14 weeks, we are also going to give you another survey, which is the exit survey, to ask on how much has it improved in terms of the knowledge of this subject. And we hope that by the end of the 14 weeks, the knowledge of this subject, your knowledge of this subject has improved. Okay, please, although I stated that it's to be completed on the 31st, please complete it as soon as possible, right after you have gone through the slides, this video, so that you won't forget to actually fill this in. Okay, so I always like to recap what we have covered, so that you are actually following this lecture from the very beginning, okay, so that you remember what you have gone through. And then so we are going to progress to another topic today. So we talk about we first describe that you need, in order to actually understand thermodynamics, that there is a system, surrounding, and boundary, and then you have different types of system, one of it being the equilibrium system, and what kind of processes do the system actually go through? Does the system actually go through? So you have the 4 types of processes: adiabatic, isochoric, isobaric, and isothermal. And today we're going to talk about 2 of them. And this is a table to simplify the types of system that you can have, which is the open, closed, and isolated. And it depends on the flowing of mass, work, and heat in between the surrounding and system. So you have these types of systems. So it varies according to this list. Okay, so today we're going to start off with the first law of thermodynamics, right? We also talked about the 0th law of thermodynamics. So today we're going to proceed with the first law of thermodynamics. So this is the first part of the lecture. So the first law of thermodynamics is divided into 2 parts, and we're going to talk about the part 2 next week. Okay, so, and I believe that this is not the first time that you have heard on the first law of thermodynamics. I'm sure you've heard about this. The internal energy may be transferred as heat or work but cannot be created or destroyed. You've heard about energy can be transferred but cannot be created or destroyed. So, and this can be uh, what you call represented in terms of an equation. So here you have the energy change, which equals to the heat energy transferred plus the work done. So what it means is that the gist of the first law of thermodynamics states that energy is conserved. So the internal energy, the U, okay, is the total energy of a system, and it is an extensive property, and as we have learned before, an extensive property depends on the size of the system. And because it's impossible to know the absolute value of internal energy, we always talk about the change in the internal energy, delta U, and which means that it is the change from an initial state to a final state. And so um, that that leads to the internal energy being a state function whose value only depends on the current state of the system, and it doesn't matter the path that it takes. So other examples of state functions will be like temperature, pressure, and density, and many other physical entities that you can also find out. Okay, so really, as I've stated earlier, so a state function is a property whose value does not depend on the path taken to reach the specific value. So uh, what it means is that you're not interested on how that state was reached, okay? And this is as opposed to the path function, in which it really depends on the path that it's taking. So perhaps this is a better representation to actually describe what a state function is. So you see here Mount Kinabalu, okay, and there are two routes that actually leads to two paths that actually lead to Mount Kinabalu. You have path A and you have path B, both leading to the Mount Kinabalu, and they have the same change in elevation, means that the altitude or elevation of mountain is the same, so it's a state function and it does not depend on the path. However, whether you choose to take A or B, they would have very different distance traveled. That means the distance of A and B is not a state function. That means the distance walked is not a state function. It depends on the path taken. It seems that path B will take a longer distance to reach Mount Kinabalu. But in terms of the elevation or the altitude, it doesn't depend on the path. And so that makes the altitude or elevation a state function. Okay, so I hope that's clear on what state function is. Okay, going back to the first law of thermodynamics, where you have this equation delta U is equals to Q plus W. Now, what's important for you to also note is that the signage for heat and W depends on whether if Q is positive, it depends, it is when the heat is absorbed by system, okay? And vice versa, when heat is lost by the system, is a negative. And the same is true for W. So it also, the signage is dependent on whether it's work done on the system or work done by the system. If it's work done on the system, it's positive, and if it's work done by the system, it's a negative. Okay, so this is very important because so make sure that you know while this equation is very important to take note, it's also important to take note of this part as well. So yeah, it's just saying that you can have so that equation means that you can have an increase in internal energy when the system absorbs heat from the surrounding, or the surroundings to work on the system, and vice versa when you have a decrease in internal energy. And the for internal energy, heat and work, they all have the same unit, which is joules. And sometimes, depending on the nature of the questions, so you need to know the conversion. Of course, conversion will be given. You're not expected to memorize the conversion. So this is the conversion for joules. So if you have a mass of 2 kilograms traveling at 1 meter per second, so this is just an example. Okay, the kinetic energy is given as such. Now let's look through an example. I always like to give you an equation at the same time, give you an example of how you can use the equation so that you know. So you know how to actually use the equation. That's the most important thing. So an electric motor produces 15 kilojoules of energy per second as mechanical work and loses 2 kilojoules as heat to the surroundings. And what is the change in the internal energy of the motor? First of all, when you are given such problem, you need to jot down what is asked and what is given. So apparently the system is the electric motor, and what you want to find is delta U, and delta U, as you know, is Q plus W. And Q has to be negative because it's the heat loss to the surrounding, so -2. And W is also negative because this is work done by the system. Hence delta U gives you -17 kilojoules. Now the next example, when the spring in the watch was wound, 100 joules of work was done on it, but 15 joules escaped as heat to the surroundings. What was the change in the internal energy of the spring? Again, the system is the spring of the watch, and you need to find delta U. Now again, it's a heat loss, so it's a -15 joules. But work is done on the system, that gives it W, a positive 100 joules. And so delta U gives you positive 85 joules. Now this increase signifies the internal energy stored in the spring, which will enable the spring to operate. Okay. Now you talk about this work, heat, and energy. Ultimately, work is the most fundamental concept of thermodynamics, because in any thermodynamics process, the interest is how much work can the system do. That is your main concern. Okay, and all measurements of heat and changes in energy amount to the measurement of work. So in some cases, you have this dW denotes the work done on a system. And again, if it's positive, energy has been supplied, negative, energy has left the system. So now, really, the calculation of work starts from the definition used in physics. And in your introductory physics class, during your high school, or maybe your matriculation, if you remember, work is equals to the opposing force times the distance, right? And so you have here the work done by the system, the opposing force, and the distance. And if force is independent of the position, that means it's constant. So you can actually find work by taking the integration of that. So that leads you, because force is constant, so you can take it out from the integration. So that leads you work is equals to force, opposing force times the distance. So in thermodynamics, if you take that analogy, so we are often concerned with the work done on or by the system as it contracts or expands. So the work done by a system depends on the volume change and the external pressure. So you have W is equals to minus P delta V. So it's almost like your work is equals to the opposing force times the distance. But this is via the concept of a what do you call gas expansion or contraction. So I also want to introduce to you the term free expansion, which you may find in textbooks or anywhere else when you read on thermodynamics. So really, a free expansion is a process in which an unrestricted expansion of a gas without any work output. So it's like you have here uh, A being the gas and B being vacuum, and you have here like the separator. So as this is before expansion, as soon as you open that, immediately the gas will fill in the whole space here. And obviously, this is a highly irreversible process. Okay, this is definitely an irreversible process. And it's also called a constant internal energy because there's no exchange of heat and work between the system and the surrounding. And so because there's no opposing force, so P is equals to 0, that means work is equals to 0, so no work is done. Likewise, in a closed system where there is a fixed volume, okay, delta V is equals to 0, so work is also 0, there's no work done. Right. So the first process that we're going to talk about is an isobaric process. And iso means the same, bar means the pressure, so you're looking at a constant pressure. So we've seen this, work is equals to minus P delta V. And so here we have a case in which you have an expansion, okay? A fixed amount of gas in a cylinder container, and the cross section of the cylinder is A. So it undergoes expansion, and the height of the gas column has increased by L. Okay, so now how do you actually quantify this? Okay, so now the volume change is, so you see here, the volume change is the cross section area times that of the height, okay, or the length here, and so that is A times L, as you can see. And force is equals to pressure times the area, P times A. So expansion work is the work done by the system, so it should be a negative, all right, according to what we've seen before. So the expansion will then be equals to the minus force times the height or the length, the height change in the volume. So you have minus F is equals to this, the force is equals to pressure times the area, and then times the length. Okay, so this, as you can see here, AL is actually delta V, so it's equals to minus P delta V. So you get work is equals to minus P delta V. So you get the derivation from the force to the length up to work is equals to minus P delta V. And what this is really is the area under the graph of P versus V, from V initial to V final. So here you have constant pressure, and you have Vf and Vi. So you see here that the work done is actually the shaded area underneath the plot. And so this is an example of a PV diagram. So PV diagram is associated to You have this for every process. You have an associated PV diagram, and for an isobaric, this is the PV diagram for isobaric. Okay, so it's very simple. You just have to work through this and just see that it's actually the shaded area. And one example that you can actually see this relationship. Okay, consider gas in a cylinder at room temperature. So say it's 293 kelvins with a volume of 0.065 meter cube, and the gas is confined by a piston with a weight of 100 Newton and an area of 0.65 meters square. So the pressure above the piston is actually the atmospheric pressure. So what is the pressure of the gas? So I've given you the conversion here, so you can expect that in a test or in an exam, the conversion is given. Maybe in the exam, not in the test. So I just want you to find out, the conversion yourself, so that or tutorials, so that you do a little homework there. So in order to answer that, so it's obvious that the weight of the piston and the atmosphere pressure exert the downforce, and so this is balanced by the upward force by the gas pressure. So the two actually equates, so that gives this force is equivalent to this force. So force is equal to pressure times the what you call the area. So PA is equals to PATM times A times the weight, and solving for P because we want the pressure of the gas. So A moves here. Okay, so this becomes just P, this becomes W over A, and you plug that into the equation, and because the conversion is 1 Pascal is equals to 1 Newton per meter square, so there's no change in the numbers here. So you'll see that the pressure, the gas pressure, is 1.0145 times 10 to the power of 5 Pascal, slightly larger than that of the atmospheric pressure, in order to support the weight here. Okay, so you can expect it to be slightly larger because there is the weight here, the force that actually push it down. Okay, right. So then the second process that we're going to discuss is the isochoric process, which is a constant volume. Now, if a reaction occurs in a closed system, we have talked about this before when we talk about after we talk about the what you call free expansion. Okay, so delta V will be 0 then, and from the equation of work is equal to minus P delta V, that gives W equals to 0. And so if you apply that into the first law equation, so that gives you delta U equals to Q, and to signify that it's a constant volume, sometimes we add the subscript V here to signify that this is heat for a constant volume. Okay, so hence the internal energy change for a constant volume of for an isochoric process is equal to the heat change at constant volume. So in terms of the associated PV diagram, because it's a constant volume, you can clearly see that it's just a straight line, a straight vertical line here because of the constant volume, and because of that, there is no area underneath this plot, and so work is equals to 0. So sometimes if an equation is not so obvious, the plot is very obvious, it screams out to you that there's no work done. So that's the beauty of having the PV plot here to actually represent this a process, and in this case the isochoric process. So pretty much for today's lecture I want to cover on the first law of thermodynamics, and please remember all the signage for W and Q with respect to whether it's work done by the system or work done on the system, heat loss or heat gain, and know what free expansion is, know the equation for work, which is the opposing pressure times the delta V, and know the two processes, isobaric and isochoric process, and the associated PV diagrams. Okay, so here's an applet in the internet in which you can actually vary certain values, certain parameters. So do play with that so that you have an idea of how a PV diagram actually looks like when you change some parameters. Okay, at least this is one that I find. I'm sure there are others that you can also search. All right, so now I'd like to leave you today with a question, right? So you have delta U is equals to Q plus W. As I've said, the ultimate what do you call aspiration is to have as much work done, like as much work done. Okay, so if you're talking about heat loss, right? Heat loss by the system. So what do you do? What can you do with the waste heat? Is there any, you have this from factories, from vehicles, producing so much heat. There's so many systems out there, thermodynamical system out there that is actually giving off heat. Is there anything that we can do with the waste heat, or is there not? So think about it, okay? On whether there's any value or any use to this waste heat. Because really, when you learn thermodynamics, the goal out there, okay, out there in the application process is actually about applying this and then, maximizing on the work. And then what do you do with the heat? So this is an engineering problem, so which I think chemists can also think about. So think about it. Now, if you're a fan of roller coaster, and if you've been on a roller coaster before, okay, you probably realize that the first hill of the coaster is always higher than the following hills. So why is that? So this is something for you to think about, so that the next time you're on a roller coaster, even if you're oblivious to that, if before that, so the next time you're on a roller coaster, you'll be more aware, of their surrounding, and realize that the first hill is higher than the following hills. So is there a reason for that? So I leave you with that, with those two questions. Okay, so that's all for today. So make sure once again to actually sign in your attendance via the QR code, which is already up in Spectrum. And again, I would like to remind you, please use please add in the slash number in your matrix number, otherwise it won't record your attendance. Okay, so thank you, and see you soon again next week for the next lecture. Thank you, and Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bye for now.